Welcome to this explainer. Today, we're diving into a genuinely fascinating evolution happening right now in the world of artificial intelligence. We're looking at how large language models, or LLMs, are essentially transforming right before our eyes. They're graduating from these passive tools that just fetch information for you into active, autonomous digital navigators that can literally browse the internet on your behalf. To really wrap your head around this, imagine a digital workflow where the core intelligence, the brain of the LLM if you will, actively hooks into the raw data of the web. It's not just reading a page, it acts as a real-time translator, converting insanely complex web interfaces into clear, actionable steps for, say, a visually impaired user navigating with a digital cane. Specifically, we're going to explore a really compelling new research paper from Politecnico di Milano that investigates how these systems, which are known as agentic web browsers, could completely revolutionize web accessibility. It's a deep dive into the nuts and bolts of cutting-edge AI and how it interacts with human-centered design.
Here is our roadmap for today. We'll start by meeting agentic web browsers, look at the accessibility paradigm shift, dive into the case study, weigh the success of fluidity and flexibility against the failure of control and transparency, and finally, look at the future of inclusive UX. Let's jump right in. Section 1. Meet agentic web browsers, what they are and how they work.
So what exactly is an agentic web browser, or AWB for short? Well, think of a traditional large language model as a really knowledgeable encyclopedia that you can talk to. An agentic web browser is more like a proactive personal assistant sitting right there at the keyboard for you. When you give it a command, the system basically whips out a digital magnifying glass and scrutinizes the invisible scaffolding of a website. It actively interprets the document object model, or the DOM, that underlying code structure that tells a browser exactly where every single button, text box, and image lives. The AWB reads that DOM, takes real-time screenshots to grasp the visual layout, and then actually translates your natural language intentions into physical interface actions. It clicks, it scrolls, it types. It takes what you say out loud and maps it directly onto the web's architecture.
Now, to really grasp the technical nuance here, we've got to put AWBs side by side with other AI models across a sort of visual continuum of capability. Over on one end, you have the rigid robot, traditional LLMs. These are entirely passive. You type a question into a text box, you get an answer back. That's it. Zero external action. On the complete opposite end, you've got computer use agents, or CUAs. These go all out. They navigate a chaotic desktop full of open windows, tabs, local apps, the whole shebang. They control your entire operating system. Agentic web browsers, they sit right in the sweet spot between those two extremes. They are highly specialized subsets of CUAs operating within the strict boundaries of a single browser window. And because they're hyper-focused strictly on web environments, they can dedicate all their processing power to smoothly handle complex web navigation while you just sit back and provide voice commands.
Moving to Section 2, the accessibility paradigm shift, from direct manipulation to conversational interaction.
Historically, assistive technologies like screen readers or magnifiers have relied heavily on direct manipulation. Picture a highly stressed, overwhelmed driver tightly gripping the steering wheel, desperately trying to navigate a chaotic, totally unpredictable road. That is exactly what it feels like to manually tab through thousands of lines of hidden code and poorly labeled web elements. The user has to meticulously inspect the layout and manually trigger every single action. It's a massive cognitive load. An agentic web browser fundamentally flips this dynamic. You go from being the stressed-out driver to a relaxed passenger. You sit back and a sophisticated AI chauffeur takes the wheel. The AI directly manipulates the interface, handling all that heavy mechanical lifting of the website's layout, while you simply converse with it. For visually impaired users, this is huge. It completely eliminates the barrier of complex visual inspection. Section 3. The case study. Testing Perplexity, Comet.
So, the researchers at Politecnico di Milano picked a genuinely fascinating subject for their exploratory case study. We are looking at a really unique intersection of extreme visual limitation and immense technical know-how. On the visual side, we have a 31-year-old male with congenital low vision. He's totally blind in his right eye and operates with a visual field of below 3% in his left eye. He has relied on assistive tech like color inversion and intense screen zoom his whole life. But contrasting that severe impairment is his background. He is a computer engineer. This overlap is absolute gold for researchers. Because he actually understands the processor-level mechanics of the technology, his feedback isn't just your basic usability report. He's able to provide highly informed, expert-level insights into exactly why the AI makes the algorithmic choices it does.
The researchers observed him using the voice user interface of an agentic web browser called Perplexity Comet. and they set up two very distinct scenarios to test different types of cognitive load. Step 1 was an exploratory e-commerce task, configuring a product on a commercial site. This kind of task is inherently ambiguous. It requires a lot of scrolling, comparing options, figuring things out on the fly. Step 2 shifted gears entirely to a highly structured, rigid, and high-stakes task, filling out a form on a public administration portal. The pipeline for both was simple but incredibly powerful. A microphone captured his spoken intent, the system converted it to text, and the AI autonomously mapped those instructions to the exact keyboard and mouse outputs needed to get the job done.
Section 4. Success, Fluidity, and Flexibility. The participant was incredibly optimistic about the system's conversational fluidity. And to understand why this is such a massive breakthrough, you have to realize that traditional screen readers are purely linear. They rigidly read a page from top to bottom, literally forcing you to listen to irrelevant menus and endless blocks of text. The Agentic web browser acts entirely differently. Its neural network actively parses the semantics of the page, which means it actually understands context. It then dynamically adjusts its conversational output, expanding or contracting the information based on exactly what you need in that moment. Ask for a quick summary of a product. Boom, it gives you a concise sentence. Ask for detailed specifications. It expands the output. This semantic flexibility creates an incredibly empowering and natural interaction loop.
Section 5. Failure, Control, and Transparency.
Okay, but we have to look at the flip side here, because the study also revealed some critical friction points. There's a really stark contrast between the fluid interaction and the chaotic underlying mechanics. On the positive side, yes, we have those clear strengths: conversational fluidity, interaction flexibility, and contextual detail adjustment. But look over at the weaknesses, and a severe lack of system transparency emerges. First off, there was a total lack of non-visual feedback during processing. When the AI was busy generating complex actions, it showed a visual loading animation on the screen, but gave absolutely zero auditory cues. If our participant hadn't possessed enough technical knowledge to understand that generative AI just takes time to think, that dead silence would have made him assume the whole system had simply crashed. And beyond the silence, the system also autonomously skipped available configuration options without even asking for user consent. It forcefully overrode his agency. And the most alarming friction point happened during that high-stakes form-filling scenario. Imagine an autonomous robot arm just suddenly taking over your keyboard and aggressively typing in information you never even provided. That is essentially what happened. The Agentic web browser autonomously inserted completely fabricated personal data right into official government fields. Why does it do that? Well, technically, it's just a byproduct of how large language models work. They are prediction engines, trying to guess the next most likely string of text to complete a task. In its algorithmic eagerness to be helpful and finish the form quickly, the AI hallucinated the data and totally bypassed the user. It never paused to ask for transparent confirmation checks, demonstrating exactly how dangerous a system can be when it prioritizes speed over supervised accuracy.
Section 6. The Future of Inclusive UX, Designing for Everyone.
To map out the road ahead, the researchers laid out several vital takeaways. First up, they highlight the absolute need to expand testing to broader demographics. We need studies incorporating fully blind individuals who lack both the residual vision and the technical expertise of our initial participant. Next, developers really need to focus on UI sliders that foster explicit user control, basically letting people dial in exactly how much autonomy the AI is actually allowed to have. There is also an urgent need to integrate auditory feedback loops, using sound to communicate processing states so non-visual users are never left in the dark wondering if the system is broken. Finally, we need rigorous comparative evaluations. We have to test these new agentic systems head-to-head against traditional screen readers to prove they represent a functionally safer, genuine improvement. And honestly, inclusive design improvements here will inevitably benefit the general population too. As we wrap up this explainer, I want to leave you with a provocative thought by looking at the broader picture of automation. Think about the trajectory of autonomous vehicles. We've spent years trying to trust cars to navigate physical roads safely. Now we're asking an AI to autonomously navigate the incredibly complex, highly unpredictable roads of the internet. The potential for agentic web browsers to democratize digital access is absolutely staggering, and transforming complex visual interfaces into fluid conversations could quite literally change millions of lives. But if an AI hallucinates on a simple government notepad form, how can we confidently let it drive the entire digital experience? As we consider the future of delegating tasks to AI, we really have to figure out exactly how much control we are willing to surrender to the machine and demand the transparency required to build systems we can truly trust.